So today we have another exciting speaker. Today is sort of the Raytheon Day. One of our platinum sponsors. Raytheon is a $25 billion company. It's a big company. So before we get started, I'd like to introduce the folks from Raytheon. You can just raise your hands. So we have a big team here. And of course, tonight we have a dinner hosted by Raytheon at Hyatt. I think it's a nice sit-down dinner, so that'll be nice. I also like to actually personally introduce Gary Summers. Gary, he is a longtime colleague of mine while he was at MIT Lincoln Laboratory, and he's been with the Raytheon for about 10 years. And I think his support for this program was instrumental in actually lining up the just a bigger platinum level sponsorship from Raytheon. So Raytheon is the sponsor for the UAS SAR project. Where are you? Yeah. Okay. All right. So you'll get to go for lunch first for that. And today's lunch is I believe it's a taco. But let's do the quick check. So race car. All right. Come on. UAV. UAV SAR. We already did that. Yeah. Cogworks, Metalytics, CubeSat, embedded security. Okay, I think I'm missing one. 3D printing. All right. So with that, I guess we're ready to get started. I'd like to introduce Annabel, who will actually introduce the speakers.
Good morning, everybody. I'm so excited to be here. My name is Annabel Flores. I'm a product line director at Raytheon. And the glazed looks you're giving me is about what everybody gives me when I talk about product line director. So basically, Bob said we're a $25 billion company, but we have all these little subsets of it. So 4 business units, mission areas within it, and then director product lines within it. So I'm a director of one. I own a portfolio of programs of radars, unmanned and manned platforms, so I've got folks all over the world. About 500 people report up to me from engineering, supply chain, finance, kind of the whole works. So that's part of my job, is to balance the development, cradle to grave, and then support our systems as we get them to the warfighter. So I'm an engineer by training. Actually went to MIT as an undergrad and a grad student, so I have a lot of affinity for this school and these programs, and I'm so honored to be here with you guys. You guys have already accomplished a lot in your short lives, so there's a lot of potential still in front of you, and this is really about helping you realize what you're going to do next. So a little bit about me. I'm from Texas. I'm a Texas girl. I love math and science, always have, and when I found out about engineering, it was, hey, we can bring these 2 passions of yours together, which I thought was really cool. It was a way to make sure that I could use my brain, but also develop some cool products, design some new things, get products out to people, and really make a difference. My sister wanted to be a roller coaster engineer. That didn't quite work out. But I've been with Raytheon now for 20 years. Don't do the math. I interned there before I started, so I know there's rumors of a very cool internships that are going to be made available to you folks. So that's where I started at Raytheon. I started as an intern just to see what things they were doing, what cool things they would come up with, and I loved it, and I've stayed ever since. The reason I joined is because I got to meet a lot of very smart, very helpful people, and I felt kind of at home. It was part of kind of belonging to that same group of, hey, I want to work with these people day in and day out. You spend a lot of time with your coworkers, so that was it. The other reason I stayed at Raytheon, or I joined Raytheon, was because we were working on some really cool stuff. I started my career as a radar engineer on tactical radars. So we were really trying to make that cutting edge new system to help our warfighters. And I thought that was really exciting. Over my career, I've moved around a lot within Raytheon, had a lot of different opportunities, worked multiple different radar type programs, manned and unmanned vehicles. I've also done EOIR, so cameras, sensors, unmanned air vehicles as well, so we get to work with a lot of the primes. Yeah. So even now, some of my radar systems go on UAVs, and that's part of what we do. The reason that I've stayed at Raytheon, and part of the reason that I think it's a really cool company, is because we continue to develop these very cool products, but ultimately to help our warfighter and ultimately to make the world a safer place. How many of you had heard of Raytheon before? That's a lot. That's great. I had not heard of Raytheon until I got into college and was trying to figure out what I was going to do. But I'm almost curious to ask how you all have heard of Raytheon. So maybe a couple folks can tell me why or where you heard of them. Yeah. Aha! Grandfather worked there, so a long legacy. We actually have a lot of families. Fathers, daughters, grandfathers, sons that just kind of keep that line going and keep that legacy going. Yes?
Through the Army.
Through the Army. So that was part of the reason I also enjoyed. I have relatives that serve in the Army and the Navy, and while I don't believe I have the skill sets to be in the armed forces, this was my way to help, and it was a way to contribute. Yes?
Like a very, very, I used to go to laser craze a lot for like birthday parties. There's a huge Raytheon building that's nearby.
Yep.
I always saw it.
Yes, so Raytheon has our headquarters, our headquarters for our entire company are here in the Massachusetts area, so Waltham. We have a very large footprint in Massachusetts, I think one of the larger employers in the state. But we have companies and people worldwide. So if you talk about exciting opportunities, if you want to do something different, I've had friends that go to Belgium, that go to Australia, that go to Korea, that go all over the world. So there's a lot of opportunity to work through that company. I mentioned earlier we have 4 different mission areas, so I'm part of Raytheon's Space and Airborne Systems. One of the groups, so if you read the name, it's really pretty much anything that's above ground. In aircraft, in space, we do all sorts of sensors, all sorts of different capabilities that I can't talk too much about. And then all the way through space, we do have satellite sensors as well that we go through. So again, a lot of really cool type of technologies and capabilities that we have within the company. Today, we're going to talk about some of those emerging technology areas. I'm a radar person, so radar is very cool, but it goes beyond that. And we've got a couple folks here, Bill and Shane, they're going to talk about their projects and what they're working on in BBN. BBN is a division within Raytheon. Really, their reputation, that's where the really smart scientists go, where they work a lot of research projects, really that infancy stage to help develop very cool things. So that's part of their contribution to how they fit within the overall Raytheon picture. And they're going to tell you about some of what they're doing. They're also the ones hosting the internship. So they're really good people to get to know if you're trying to find out a little bit more about what it's like to work at BBN. Let's see, anything else? Yeah, I think I covered it. I do get a chance to talk to the UAV radar folks a little bit later, so we can talk a little bit more about what that's like. But you have an exciting day ahead of you. Great program overall, and hopefully you'll enjoy the Raytheon Day. And with that, I'm going to hand it over to Shane to talk about his project.
Thank you for the introduction, Annabelle. Now that we're a minute away from it, since I was futzing with the AV equipment. So as Annabelle said, I'm Shane Clark from Raytheon BBN Technologies, and I'll talk a little bit today about the topic of swarms and how a human can work with a swarm, a single human specifically, which I think makes this considerably harder. Okay, so first thing to answer is, what is a swarm specifically? So if you look up sort of dictionary type definitions, the generally agreed upon definition is more or less that a swarm is a large number of something, usually insects, typically moving and typically densely packed. So as opposed to a collection of people or other agents or animals that are distributed over a large area, swarms specifically are focused in some way on density. And the way that I think about a lot of this, hopefully you guys play video games, otherwise none of these analogies are going to work at all. But the way that I often think about this is, for example, in StarCraft, if you're a Zerg player, then you need a lot of Zerglings to Zerg rush. So here's an example of a swarm, and I'll sort of stick with this StarCraft analogy because I think that it's one of the better examples of the sort of thing we're actually trying to accomplish here with real platforms and in simulation. So one good question is, what is a swarm good for? Zerg rush, I already gave that away. The idea here, if you're a Zerg player, or if you have a swarm of anything, maybe you're honeybees protecting a hive, is to confuse defenses and to just overwhelm whatever you're going after. That's a typical use case that you think of in the context of StarCraft or in the context of bees, et cetera. Of course, that's not all they're good for, right? So honeybees are not typically considered to be swarming when they're moving about in the hive, but at that time they're still working cooperatively in a huge number in a dense area, right? There are many, many bees in a tiny hive. An example of how this might map to something that you'd see in the robotics space, in this case specifically UAVs, is, let's say, search and rescue, or mapping. If I would like to survey or otherwise search this large space, I can do that much more efficiently if I have multiple agents to do it. And the question is, how much of an efficiency gain can you get, and sort of what are the barriers to achieving the maximum efficiency? So ideally, you would like to achieve at least linear scaling with the number of agents you assign. Now, we know for a fact that won't happen with humans, because if I'm coordinating search and rescue with humans, then one person is going to sit down with a map, and they're going to subdivide the space, and they're going to manually assign people to segments of the space, and those people may or may not search those areas at the same rate. They may not report their progress in the same way. If someone trips and twists their ankle, there's no contingency plan in place for who can most efficiently replace that person for their segment of the search. But these are all things that potentially we could solve with a swarm. There we go. So what makes swarm control hard? I already talked a little bit sort of informally about what makes it hard to control a large number of humans, but if we have a swarm, then there's a lot of really tight time constraint coordination we need to handle. In this case, we have banelings. They react immediately. They always do exactly what you want them to do, right? And so the only limit, practically speaking, is what StarCraft players call their micro, right? So you got to get your actions per minute up to micro your banelings and maximize their utility. But all of these problems are totally exacerbated when you're dealing with more realistic platforms. And as an example, if we look at a simulated swarm, so this is a video from a simulator that we've built designed to simulate swarms of air and ground vehicles. This is really hard. So, someone's driving this from basically the Unreal Engine editor interface, and it's really hard to select units. It's really hard to move them around. You have a free camera in free space, but it's not easy to move. And because this wasn't engineered by someone to make it easy to see your units against the backdrop, it's hard to see where they even went, right? Because the background is gray and white, and the units are effectively gray. So things get really difficult really quickly. That's just from the perspective of sort of selecting and understanding what they're doing in simulation. Things only get worse from there when you move to real platforms. So these are some small ground robots that we've built. And these are modified commercial off-the-shelf robots. When you get into a tight space, all of a sudden, all of the reality of obstacle detection, obstacle avoidance, movement coordination really kind of hits you in the face. And in the case of this video, come on, cycle through here, it's a cool shot, but it's a cool shot because we set up a camera to get all of the robots turning, and we didn't know which direction that one was going to turn in. So it turns out that it went towards the camera and just smashed that GoPro tripod and pushed it across the floor. Because you don't have perfect information and perfect control over all of these things in real time if you want them to help you at all by having some sort of intelligence or otherwise non-deterministic behavior. So I'll talk a little bit about some ways in which we can try to make this a little bit easier. First of all, smart platforms help. This is a really, obviously visually unimpressive simulator, but it's one that lets us do large numbers. So this is 36 simulated UAVs. They're flying from the BBN office over by Fresh Pond on the west edge of Cambridge to the International Departures Terminal at Logan. just as an example of a flocking behavior. And while this is a low fidelity simulation, in this case, they're a little smarter, right? So these have, because we get to do this in simulation, perfect knowledge about where their neighbors are, and they can coordinate to stay in a single unit, to fly together, to not run into each other. And in fact, they implement sort of a spring forces model where they try to maintain spacing to their set of neighbors that achieves approximately some mean target. The trade-off with something like smart platforms is, of course, that when they're smart, they do things on their own. And you need to be able to predict what they're going to do and achieve the correct level of smarts, right? So my ground robot that drove into the GoPro was smart. And I left it up to the platform which way to turn when I tasked it, and it made a decision I didn't like. You could see that being much worse if we're dealing with something other than a GoPro, right? Maybe I have 5 of those, and they're much more expensive ones, and they all turn into each other, and their obstacle detection isn't fast enough, so they just slam into each other. Maybe their obstacle detection works, and they all turn toward each other and freeze, because they're smart enough to not run into each other, but not smart enough to work out what to do next, right? So they achieve like a physical deadlock. And so there are a lot of problems to work out in that space. Another thing that helps is sort of flexible views of the environment to let the human really get a sense of what's happening with the swarm agents. So let's say you have 200 of them. You cannot individually recognize and manage each one, right? Visually, it's difficult. In terms of cognitive load, it's impossible. So this is an example of a LiDAR scan we took of a test space. Excuse me. Actually, the test space that I showed the robots in before. And if you have a nice LiDAR, then you can get color too. So this is a colorized and downsampled point cloud of that space. And one of the things that we've been working on there is creating an environment where we can embed that 3D model in virtual reality. So this is an early prototype where we have an HTC Vive interface, and you have a sort of disembodied camera view, much like StarCraft, and you can use the controllers and gestures to pan, tilt, and zoom this map area so you can see, for example, is my robot in one of the buildings that's in front of the street, or is it in the street? Because you need to be able to disambiguate that, and you need 3D information to figure it out. So this is something we've been working on in terms of just getting you a sense of where things exist in the environment. And the final bit that I'll talk about a little bit is communication, which is still really challenging. Because once again, if you have smart agents or you have people who think they are smart and assume a lot of context, then you're going to have a lot of mismatches. So the other thing that you can do to task agents in this environment is you can talk to them. So you might say something like, search that building. And then you have to answer lots and lots of questions. And you need to answer them either automatically from context, or you need to account for how you're going to give that intent to all the agents you're dealing with. Right? So I say, search that building. I didn't designate who should search it. I didn't designate what they need, right? Can they use a camera? Do they need a LiDAR? Is it at night, so they need an IR camera? Which building specifically? Did I gesture to something in the VR environment? If I did, are there buildings that are behind each other? So I need to somehow disambiguate which building in that row it is. How quickly should they search, right? So you're going to trade off the thoroughness of the search potentially with speed, and they don't know what your priority is. What are they looking for, right? Are they looking for a person? Are they looking for an object? If they find it, are they done, or do you just want to map the building, right? Do you want to know everything, or do you have a specific goal in mind? So the list of questions sort of goes on and on for what you might actually need to do with these swarm agents. And so that's just a little bit of introduction to some of the problems we're thinking about around swarms and how a single human operator can learn to deal with a swarm, both in terms of how they can clearly communicate intent in a way that they find somewhat natural, and how they can actually monitor and have a good sense of what's happening with their swarm so that they can coordinate next actions. Thanks.
So I'm Bill Ferguson. I'm what's called a lead scientist over at Raytheon BBN Technologies. We're just across town, I guess, that's been established already, over by LYFT station. And I hope some of you will get a chance to come over and see some of the cool stuff that we're doing, because I think there's lots of things there that are worth seeing. I'm going to talk to you about a project that we're working on in an area called explainable artificial intelligence. And this means trying to get principally machine learning based systems to be able to explain the choices they make to ordinary people. And we'll see how that goes. Let's see, okay. Yes, good. So here's the team, and I don't want to start without giving credit to the other people involved. There's some of us folks from over at BBN. We have professors from Georgia Tech. We have a team here with Antonio Torralba right here at MIT, and we have a team over at UT Austin. So there's lots of cool researchers working on this, and we're kind of at the fuzzy edge of trying to figure out what's going on. Now, before I start, how many of you here know about machine learning and have worked with it somewhere or another? Yeah, that's what I thought. Lots. Right. Good. Do words like deep nets, convolutional neural networks, recurrent neural networks? Okay. Unfortunately, I'm not going to use any of those words. I have weeded out most of the deep technical content, but it will tell me what to expect you to laugh at when I try to explain what is going on. Come on. There we go. So here is machine learning completely explained in the world's most glib explanation, but it'll give some context for people that don't know particularly what's going on. So first of all, I'm going to summarize all machine learning as neural nets, and then I'm going to talk about all neural nets as deep nets, and then I'm going to talk about all deep nets as those circles and lines up there on the screen. So with that said, what an ML system is basically doing is it takes input from something. And in our case, that'll be images, but it could be radar systems, it could be bank account data, it could be anything. Feeds it into a bunch of interconnected nodes in the middle, and those connections have various strengths. And then when that data is fed through all that network of strengths and the nodes in the middle light up when they get energy and pass energy on to the next layers, finally at the output side, the decision makes a choice of something. Maybe it says this is a zebra, or maybe it says no, you shouldn't get this loan. Okay, but what it can't do is tell you why it decided that. In some sense, it doesn't even think. It's just passing strengths around these networks. And by the way, the trick to training that neural net, right, is to present it with a piece of data and then show it a piece of the right answer at the end. And if it gets the right answer, then you make all the connections that led to that choice a little bit stronger. And if it gets the wrong answer, then you make all the connections that led to that choice a little bit weaker. There's reinforcement learning and all you need to know about that. But it's important because it's trained on 100 millions of examples. And so when it makes a judgment, it has no clear way of indicating how it came up with that. It can't give you a satisfying answer. Now, why does that matter? Why do we care about explanation? Does anybody have a guess why people would want a machine learning system? So it's making good choices. It's almost always right. Why do we want it? Why do we want explanations for it? Why would that help? Yeah, just shout out here, right? Go ahead.
Well, if you had maybe a system that would tell you if maybe something was a threat or not, before you maybe like you launch a missile that or something, you want to know the reason why the system told you it's a threat, so you can actually really achieve security.
Yes, right. Two things there that you said. You need rationale to be able to make an argument, and you need trust. They're used to make all kinds of useful choices. They pick out images on Google. They help with medical diagnosis. We're trying to get automated cars to work. But yes, you want rationale and you want confidence. Anything else? Yeah.
So with the machine being able to explain, maybe it can pick up patterns that mostly human researchers does not. And with this pattern, we can utilize those to further research studies and look at specific points why this pattern leads to this result.
Yes, right. In other words, the explanation might actually provide insight. It might tell you something about the world that you didn't realize when you were looking at it. And that's an important function. I'm going to jump ahead now to kind of what's there. So first of all, that notion of just clarify. Most of the time when somebody asks us to explain ourselves, they're trying to figure out what it is that we're saying. Secondly, to persuade. If you have an explanation, you're more likely to believe the image. And it turns out that if you give people music recommendations, if you can give them a reason why they gave the music recommendation, they'll also more likely to pick it, even if you were a trustworthy source to begin with. There are legal and ethical reasons why explanations have to be given. And explanations help engender trust as long as they're true, worthwhile explanations. And you want them to engender appropriate trust. If the system's going to be incompetent in some situations, and most of them are under certain circumstances, the explanations will help you figure out when it will be. Sometimes we human beings give explanations to be polite, and machines may need to do that too. And so in some circumstances. So that can be a function. And then finally, my favorite, and the one that you brought up, is to actually collaborate. We explain things to each other to teach each other stuff. And hopefully we make decisions together through our explanations that are better than either one of us could make otherwise. Okay, so let's take a look at some of the rudimentary explanations that we're getting right now and what's going on. So we showed a machine learning system that could caption things, to caption this picture, and it got a baby holding a toothbrush in its mouth. Not bad for the state of the art in captioning, not exactly right. And on the right is a simple explanation. This is called a heat map, and one of the forms of explanation we give is simply for the system to show what part of the data made the most difference to the answer that it came up with. And it turns out that's a pretty good piece of explanation. It combines well with other pieces. So there we go. It's looking at the toothbrush. It's looking at the kid's mouth. That's pretty good. Here's another one. We forced it to use the caption, a young boy is holding a baseball bat. And fortunately, these systems are completely gullible. And if you force them to give a different answer, they can now explain why they gave that answer. And that's true for some interesting engineering reasons that I won't go into right now. But its explanation now, it said, well, that thing. And maybe what's going on here is that the toothbrush looks sort of like a baseball bat. Maybe. We don't know, but it's a place to look. And the data starts off and gives us some way to begin to look at how it's making those choices. Now, here we are with a loss. We asked, is there a baseball bat? And the system said yes. We were interested in why these confusions were occurring between toothbrushes and baseball bats for reasons that I don't need to explain either. But anyway, but look at, the answer is wrong. And when we look at the explanation looks like garbage. Does that look sort of like a baseball uniform? I don't know. No idea. But I wouldn't trust this answer, and that's probably a good idea because it's wrong. And lots of times the explanations, when they look irrelevant to what's going on, are a clue to the fact that the system's not with it on this particular problem. Okay, so what do people, now I'm going to change gears a little bit here and talk about what people do when they explain things. When we were looking for a theoretical way to kind of motivate our research and get money from DARPA to look at it, we went back to kind of theories of what human beings do with explanations. And they teach, they persuade, and EQUIS, by the way, is the name of our system. It's the explainable question answering. So that's kind of what we did out of that. And we said that when you're teaching big things, you have the students work problems. You sometimes tell them stuff directly. That's didactic training. You show them examples to help them work through it, and you often work them through common misconceptions or problems that students often have. So, and when you're persuading people, you persuade them with data or graphs. You give them kind of a gestalt sense, like there's lots and lots and lots of this, and that sort of thing. And that has a persuasive impact on human beings. Sometimes you use logical arguments. Sometimes you use cases. Sometimes you set up straw men, and you say, well, if it was this, then obviously this other thing would be true, so it must be what I think it is. And what we did is sort of combine those and say, what can we do with machine learned systems to help them do that? Well, we can show heat maps of what mattered, and that's sort of like a problem for the student to work out in the teaching case, and it's sort of like that gestalt sense of what's going on in the persuasion case. We can name the items in the image that we recognize that led to the conclusion. I'll tell you a little bit about how we do that. And that corresponds to didactic or logical arguments. We can show show examples from our training instances that are similar to the case, and that helps. That's like case-based arguing or examples in teaching. And finally, we can say, well, I thought it was a dog. I would have said it was a cat, except this does not look like a cat's tail. And if you can do that sort of thing, once you have rejected alternatives, you can use all these other methods recursively to amplify the explanation you get out of that. Now, a little bit about the technology, and this slide is deliberately obscurely complicated. Don't try to work it all out. But the right half came from MIT's website on net dissection, and the left half came from Georgia Tech's website on guided grad cam. But basically what this says is Georgia Tech has worked out a way to trace back through neural network systems and figure out what parts of the data mattered the most to what's going on. That turns out to be an interestingly hard problem in spite of the fact that it might seem easy. There are mathematical reasons that has to be done carefully, and we're still not that great at it, even though it seems like a relatively straight problem. And then from MIT, what we're getting is the ability to look inside these deep nets, and we find that many of the nodes in there have names, that if you teach a network to identify scenes, it will have a node inside that will correspond to cars, a node for people, a node for green, a node for sharp, a node for rough edges, and you can find those nodes and name them. This is an odd analogy, and nobody knows how powerful it is to the idea that we have grandmother neurons in our head, or neurons that become excited about specific categories. But it looks like for many architectures, and some more than others, that they also have meaningful nodes internally. Well, it helps a lot when we're trying to build explanations. Okay, I don't know how long I've been talking here. Anybody else know? So I'm almost done. I want to give a few examples of kind of where we are now with the best that we're doing. These now are from a system from right here at MIT. So here's a beautiful example. And this is combining two of those explanation modes that I talked about. The AI thinks this is a street, and then it will name the components and show a heat map of where those components appear in the image. So it says it identified window panes, it identified the road itself, it identified parked cars, that's good. It did find a mini bike, but you'll see it had a lot of trouble localizing it. There's reasons why that region is funny shaped, but again, not going to go into it now. Another example, here it's not doing so well. Gets the right answer. It thinks this is a repair shop. It thinks there are bumpers, yeah. Rim, I don't know. It's got a lot of the car there. That doesn't look like the tire rims to me. If that little awning is a service station, well, maybe it is. I mean, that's kind of like cool that it picks up that it thinks that awning is a service station awning. And finally, it thinks something is a television camera. I don't even know what. But it's a good example of here how we're beginning to look at this and say, yeah, win some, lose some. And especially we can look in here and then to figure out how we can help the system do better. And then I thought I'd finish with a picture right here at MIT. I don't know if you guys have been to the outdoor amphitheater here. Really nailed this one. It thinks it's an amphitheater. It says there's a grandstand. That's right. It says there are stairs. That usually goes with amphitheater. It says there's a sky. And notice that it's got some buildings there, because if you just find a blue patch in the middle of a picture, that might be water or something else. But if there's buildings, a line, and blue, that's sky. And then, wonderfully, it thinks that ruins go with amphitheaters, and they do, and it thinks that MIT's buildings should be accurately characterized as ruins. And I thought, good job, AI. Sometimes they even make jokes. So thank you very much, and feel free to ask more about it. Okay, so I think we're going to take questions for a few minutes. There are going to be a lot of them, so we'll do as well as we can pointing.
Questions,
what?
You answered the
what?
questions.
Okay, yeah, that sounds good. Do about as well. Back there in the maroon shirt, yeah? Yeah.
You said that you work at a division of Raytheon, right? Like something technologies. What was that again?
Oh, that is, I call it now. The old name is BBN Technologies. Now we are Raytheon BBN, but it's just BBN. You can look it up. We've been around for a long time, and now we're a proud part of Raytheon. But we do, as Annabel said, we do a lot of fundamental research and a lot of front edge research as opposed to doing something useful. Right. Over there, yes? Yeah.
Yeah, I actually have a question about your AI, like the machine learning process. So going back to a baseball bat example, baseball bats and pictures, right? We usually see them outside being used, but how is your AI able to differentiate, like taking a picture of one indoors or something like that? Like how exactly do you go about solving issues where the AI uses the background more than targeting the actual item?
Yeah, it's a good question, and it comes up for explanation too, because it is true that sometimes you identify the object from the thing itself, and sometimes you identify it from the context that it is. But ironically, the backprop algorithm that has passed through the net doesn't really differentiate between those things. So we arbitrarily get components that are identified that are actually components of the things, like the dog's leg and the dog's head. But we also get the grass, because when people photograph their dogs, they're often on the grass. And you're also pointing out something else. A lot of this comes from sample bias. So we are learning about the world that people take pictures of, which is fairly different than the world we see most of the time, because it's not all picture moments.
Can I comment on that too?
Yeah.
So another thing related to sample bias, right, is that you care about the target application, right? And Equus, I think, is designed to be generic, right? But if you isolate baseball bats by cropping them out of a bunch of pictures and you train it on the specific shape and color of a baseball bat, then you're creating sample data that's not likely to actually be reflected in your test data that you evaluate on later. And so you have to be careful about attempts to do things like focusing with a black box.
Thank you.
Yellow shirt?
How fast do you teach it to identify a new object? So time frames like a few milliseconds, or does it take a week of showing it a bunch of pictures of something before it can correctly and pretty accurately identify that something is a pixel bad?
Okay, that's a good question, but it takes a little step back. These systems are kind of trained all at once, and they'll be trained on many examples, maybe hundreds of millions, at least hundreds of thousands. And they see all those examples, and then they're as good as they're ever going to get. They don't learn anything new from that point forward. Now, there are new technologies that are enabling some of these systems to learn new things through what's called one-shot or zero-shot learning. But typically, right now, they don't learn new things. So they're going to have the explanation they have, and when we need it to learn a new thing, we throw in 10,000 pictures of that new thing, retrain it, now it knows about the new thing too. And that can take anywhere from an hour to weeks on multiple GPUs out there to do, depending on the size of the data. In the back center? Sorry, in the blue shirt. Yeah, I have a wandering eye, so it's impossible to tell who I'm looking at.
Regarding swarm systems, when designing a swarm system, where do you draw the line for what should be processed on an individual agent versus a central server?
That's a really good question. So in our particular case, we're interested in the swarm being scalable in sort of the face of various dynamics that might happen in the environment, right? So we'd love to be able to add or remove platforms in the middle of whatever you're doing. And for that reason, we bias ourselves toward doing as much computation locally as we can, but there are limits in terms of, hardware cost and battery power mostly with that. So for example, some of the fancier platforms we have a Jetson TX2 on them and can run some vision algorithms. A lot of them have Raspberry Pis. So you need to balance your trade-offs there.
Okay. Do you main Xer?
I'm a Protoss main. I'm terrible.
And the second question is, so you spoke about the user interface, which is really important for having one person interact with this one. What made you gravitate towards the usage of virtual reality? Is it because it's the new hot thing right now, or is there a reason you chose that medium over other?
Yeah, so we felt confident that, the idea of just sort of 2D imagery was not going to get us far enough, and that we need to be multimodal or somehow more immersive. And so when you look at that, the two big options are sort of AR approaches and VR approaches. The thing about AR, which is really cool, is that you can keep looking at the real environment around you and have stuff projected in it. But when you're dealing with a large number of platforms in an environment that has depth, we thought that there were a lot of limitations there. So you have a row of 10 buildings, each of them has 10 robots in it, how do I disambiguate that in an AR interface? So we felt that having a VR interface where you can freely change your own perspective to adjust it as you see fit would be more appropriate.
Get one over here. In the back, gray sweater? Yeah.
My first one is when you like your neural net like gets the right answer but has one of those like wrong explanations, do you still like try to, how do you like train, like sort of like get rid of that contributing wrong factor even though it like produced the right answer? And my second question is in the swarm, in your swarms, when you have two agents that like come up with two different different answers on how to complete a certain task, how do they resolve those like conflicts, and how do they carry out the task?
Okay, we can chain this, right? So the first question about AI. First of all, the thing I'll say is that we're not primarily interested in correcting what we find in the system in this particular research. We're interested in getting the explanation in the first place. And then it's a subtle question as to what it means when you get data that seems wrong. It really might be correlated in the data. Dogs might really go with grass, or garages might really go with that node called rim. But the question is that node mislabeled? Should it not be connected to garages? There's a lot of things that might be wrong that are making that happen. So I suspect that like our explanations to each other can sometimes be fairly flaky or made up after the fact. It's okay if machine explanations aren't entirely comprehensible, as long as they're mostly or partly comprehensible so that you can understand better about what's going on.
On the swarm topic, so one of the aspects of this that I didn't talk about at all is that the way that we are programming them is actually using an aggregate programming language. So it's this sort of pseudo-domain specific language called Protolis, which is the ancestor of the proto language, which was invented here at MIT. And what you do in general is you coordinate with whoever you can talk to in one network hop, and you come to consensus on things. So for example, that grid that I showed for search, if we're splitting that up in our algorithm, then everybody will come up with a list of assignments that they like, and they will quickly, in a limited time frame, come to a consensus on what those assignments should actually be before they start executing it. But it's fully decentralized in agent to agent. White shirt?
So you said before that the machine learning system can be used to teach other people and other humans in general. So do you think as the technology itself develops, do you think you'll be able to implement it into like an education district and like implement it in schools not only to teach children about like the technology itself, but also to teach the machine learning as well? I mean, like just decision making as well.
Well, there's a lot of room for speculation there, but it just so happens that my group does a lot of training technology, so I have thought about some of those questions. And there's at least two things that could happen there. One is that the machine may have acquired knowledge that if it could explain itself, it would actually be able to teach people, whether they were students or experts. It might have noticed things that they don't notice, so the explanations might provide insight directly. I haven't thought much about what it would mean to incorporate that into a curriculum. But the second thing is that these same kinds of machine algorithms can be used to watch students, and they are used to watch students, and to help diagnose problems. And in particular, they're wondering right now that if you take enough students and enough teachers giving explanations and dealing with problems, could you turn that into some kind of gargantuan data set and train a system on that so that it would automatically say something useful to the students? Now, if that system couldn't explain itself, it might babble a lot. But if it could also explain itself, then the students might take it because it would seem that it knew what it was talking about when it gave them advice.
So with your machine learning, are you researching how the individual nodes that you find are making those decisions, and what data set has been trained to that node, and to kind of focus your initial data set?
Let's see if I'm following the question. Yeah, try me again if you've got it.
With the nodes that you've determined are saying pathing through a baseball bat versus a toothbrush.
Yeah.
are you looking into which items in your data set that you're training your neural network on are making the biggest changes of that node and trying to put on in your initial data set?
Yes, I mean, that's what we're doing when we're giving an explanation, is we're looking at the nodes, not necessarily the most activated nodes in the networks, but the most crucial ones for determining that decision. So it may be that some node in the middle was only middling activated, but that was it. If that node was a little bit different, it would have been a cat instead of a dog. In which case, then we want to get that ear node or that black node, or maybe it's, unfortunately, sometimes it's a nameless node, and incorporate it into the explanation. But that's what we're trying to do in that. Up and behind in the bluish shirt, yeah. Sorry.
UAVs, for instance, how do you deal with computational limitations when forming a consensus when you have a large number of, say, UAVs or units at that time?
Yeah, so that's something that we're still working through the trade-offs on. One of the great things about trying to do swarms of mobile platforms, right, like air and ground vehicles, is that we can adjust their density if we really need to make problems easier or harder. So one of the ways that we do consensus is we have one node elected to be the decider at the end of the consensus period, and they will dictate what the answer is. And that's an option that makes sense if you believe that one won't drop out of the sky randomly while you're trying to make the decision. There's also other algorithms for it. There's one-shot consensus, where they may or may not actually agree, but they only require one communication round, and they will mostly agree, and maybe you can tolerate that in some cases. If what they're trying to agree on is which part of a building to search, then hopefully you at least have obstacle detection and avoidance code so that they won't slam into each other when they try to search the same part. But at some point you have to tolerate some non-determinism or some potential failures in exchange for the flexibility.
How does your explanation or your heat maps take form when it's not when the machine learning system you're training on isn't taking pictures as an input? Maybe it's taking lots of numbers, or maybe like a book or something. How do these explanations form when they can't just highlight a piece of the picture and say, here it is?
Well, if I'm reading you right, we always do start from a picture, so we can highlight whatever it was that made the network make sense out of that picture. As you see, sometimes it's uninterpretable or it seems like nonsense to a human being. In fact, right now it frequently does. But we can always tell which pixels in that rectangular region caused it to pick the category that it did end up picking.
So the question was, in a different domain where your input is not, right, an XY set of pixels, like say you have a text sample, is there an analogy? Or is that in scope? Yeah, if we weren't dealing with image data, and we've thought about them some, if we were dealing with radio frequency data or radar or even something that's one-dimensional like sound, we still are going to want to be able to say these are the parts of the data that mattered most. And if it read magazine articles and it based its decision, on something in the magazine article, you'd kind of want it to highlight the words and phrases that mattered the most. In most cases, the data will have intelligible parts. And if it's not chaotic data, there will be some structure, and some parts of it will be more important than other parts of it. So I think that'll hold up, but it isn't going to be as useful in some domains as others. Black in the center. Yeah.
See a system like the one you're researching can be applied in real life?
Well, these AI systems make decisions really fast. It may take, hours or weeks to train them, but typically they come up with their answer in seconds or fractions of a second, depending on their structure. And the explanations that we are adding, it is a real concern to us that how long it takes to generate the explanation. Although at this stage in our research, we're not principally worried about that. But there are applications where you need an explanation and you need it now. now, and that will eventually become important. But the decision-making of neural net systems is typically pretty fast. You know that it's not always as real-time as you want it to be, but for us, it's plenty real-time enough. We just aren't concerned, right? Yep. Oh.
Right.
Yeah. Go ahead. You caught me. The AI doesn't actually make jokes. Yeah, right. We see what it does as a joke. I mean, when it calls the buildings at MIT ruins, that is both wrong, fortunately, and kind of vaguely you can kind of see why it seems that way. And I think that's why it's funny. There's actually a lot of research on what it is that makes jokes funny and how they work. And usually it has to do with there being two competing interpretations of what's going on that kind of tickle the brain in a certain way that we find amusing. Boy, there's a technical explanation. But at any rate, I think it's very possible for machine learning systems to produce the raw materials to make jokes because it's easy for them to see and simultaneously process those competing hypotheses about what might be true in the data.
Purple shirt in the, yeah.
So about these forms, though, how do you deal with the different response times? When you've got to control maybe multiple UAVs at the same speed, at the same time, if you don't coordinate this properly, then they're just going to crash into each other. But how do you deal with different reaction times to these messages?
Yeah, so a big part of dealing with reaction time is setting expectations from the user perspective with the granularity at which you can control them, right? So the granularity that I can control them with by design is to say something like, flock over there. And I have no ability to adjust their sort of moment-to-moment movements because if we think about a realistic network, then just the communication delays and processing delays are going to make that implausible. So what they do instead is just exchange positions with one another and try to maintain a safety margin space that will stop them from crashing into each other with high probability. I haven't had one go rogue and just fly through the formation and crash them yet. But I'm really curious sort of how they'll react, right? Like how robust the detection and innovation will be in that case. One more? Oh, Bill, it's up to you. You're the lead scientist. You're very important.
Yeah, right. Red, back again.
For machine learning, you mentioned that there are a lot of times when the machine will provide an explanation that doesn't make sense. Have you considered feeding all those sort of mistaken / ununderstandable data into another machine learning sort of situation and then try to have that one give an explanation why they're coming up with wrong data?
It's actually a good question. I mean, first of all, if you were going to take that particular proposition seriously, you'd have to have a whole bunch of explanations labeled as good or bad to begin with. And then you'd have to have something else try to learn why they were good or bad. Something very similar that we are doing, or not our team, but a different team is doing, we don't like this, but I'll tell you about it anyway. They are generating explanations by looking at lots of explanations that people have given for why a certain answer might be given for a picture, and then they generate a very pleasing explanation. And they generate nice, articulate explanations for why the system might have made the choice that it made, but we decided we wanted to generate explanations that were also true as well as satisfying. And I'm mocking them a little bit, but you know, it's pretty easy to come up with an explanation when somebody says, "Why are you wandering around staring off into space?" But the real explanation may be totally unfathomable, and we want to try to give the real explanation in these situations. Okay, thank you.
We have time for a few more questions, but I'm going to actually ask a question. So from that corner way back there, can one of you ask a question? One of the girls?
No.
So I'll repeat that question because I'm not sure many people heard it. But the question was, what's the motivation for using swarms as opposed to one super powerful agent? Because it seems like swarms add complexity. Swarms definitely add complexity. And the goal of this work is actually to figure out in what cases swarms are worth using for what. An example that I think swarms are pretty clearly beneficial is like the example I gave of search a building, if we make a few assumptions about it, right? So let's say that we have multiple flying platforms and that they know how to get through a window. If that's true, then seeding a search from 4 or 10 different locations on different floors is a huge advantage that the more powerful platform would have to be way more powerful to try and make up for. And so the motivation is things like that, where the task is sort of intrinsically parallelizable.
Do we have a question yet back there? No? Go ahead.
So the swarms are going to be implemented in real life in October. I have a deadline to do a field demonstration. I only need to field 25 of them, but I will take real air and ground vehicles outside with a single person in the VR interface and see what happens.
So actually, so question for way back. The ladies team back there. And the girls come out. There you go. Okay.
Data that is not image, so like waves, a signal to me, what other sources of error can there be such that the neural network gives like a bunch of
I didn't get all of the last of that question, but I'm following you in general. You're wondering about non-image data and what kind of errors arise. But what was the last part that you said?
network predict just one label instead of like the correct one. Like that's what
Well, first of all, these neural networks, I vastly oversimplified them, right? Oftentimes they're doing more than making a single categorical choice about what data they're looking at. Sometimes, if a machine is translating, then it's going to produce a stream of words coming out when it gets a stream of words coming in. And this process of explaining what's going on changes a little bit because you may have to explain each aspect of the output that was produced. So if you're listening to an audio signal or something and turning it into words, and you wanted to explain what was going on, you would want to explain why it was that you thought that this was the word box or something, and that would have to do with both the sounds that were occurring during the time that was spoken and probably with the neighboring words and sounds, because when the words before it were what's in that makes it more likely that this word is going to be box than fox or something like that. So again, what you want to do is get the components that mattered and explain each of the phenomena, each of the choices individually.
So I think they'll be here for more Q&A.